Good evening and welcome everybody. This is Obi-Wan Pez4 and Simplex Pachinko. We are doing some math tonight for differential equations. This is class... Oh no, I forgot to change the... Oh. I forgot to change our information. It's still on random doing stuff from last night, so... Class time. We are on night 10 of differential equations. Kind of hard to believe we're already there. Hey Laz, how's it going? And for everybody who is in chat, we're going to welcome to the stage, as usual, our two awesome co-hosts. We have tonight Enstucky and eat of the two eye pie, Zach. So if you would like to introduce yourself, go for it.
I'm Ian Stuckey. I was here last week, took a break on Monday, back again. I'm not entirely sure what's coming up based on because we did Unhomogeneous on Monday, but excited to find out.
Woohoo!
I'm Zach. Y'all know me. Let's be honest. Y'all know me and Stuckey. I mean, we're here almost every time anyway. So, but I'm here. I'm here to once again attempt to do some stuff with differential equations today.
Alrighty, my hands are just flying over the keyboard right now because I have no idea what I'm. No idea what
It's
I'm
improv.
calling
Just
this
like
one.
you gotta play yes and. That's all it is. Yes and.
Yep. Here we go. All right, so it's gonna be a surprise to everybody. So yes, that is right. Tonight we are going to talk about variation of parameters as it relates to first-order systems. And this is, again, without the context that everybody knows and loves of the second-order differential equations. So at the moment, we're still just talking about first-order systems. I am planning on, in the probably next week, starting to link in all of that really cool stuff about how first-order systems can be linked into second-order differential equations. So it's going to be kind of like next week is going to be the big one to make all of the connections between the two. And this is where it gets really exciting. Alrighty, so unless anyone has any further ado,
I think I'm good.
I'm fine. Let's go.
So using the methods that we talked about last class, how would we solve the following differential equation?
Perhaps turn it into matrix form first, look for a homogeneous solution, then make some inspired guesses for a particular. Try to figure out what the remaining coefficients would be.
Alrighty. So, come over here. Yep, cool.
I'm confirming that all of those coefficients of x1 and x2 are negative.
Yes.
Okay, because like one of them looks like sort of a squiggly, and I wasn't sure. It's a little blurry. That's all.
I think it had some error with the scaling for some reason, but yeah, they are actually all supposed to be just negative values.
Very good.
So, -1, -4, -1, -1. Alrighty. Yep, this evening the family and I were watching most of Captain Marvel, so we This is the kids' first foray into the MCU.
Wish them the best.
Yeah, we decided to do chronological order rather than chronological release order. So it's of the setting of the movie itself. Might make it a little confusing, but you know what? It's fun.
I don't think those films were built to be watched in chronological order.
Probably
in that
not.
way. I don't think that was the design choice from Marvel. But
Nope.
Anyway.
It's gonna get pretty rough here in a minute, but you know.
Yeah. Well, okay, so we just need eigenvalues, I guess, for the homogeneous solution.
Right. So in this one, we're looking at -1 minus lambda, -4, -1, and -1 minus lambda.
Yep.
And we would like this to be what?
Singular, so
Right, so we want our A minus lambda I to be equal to 0 in order to make sure that, again, we have linearly independent solutions at the end. Alrighty. What do we get?
Well, so
determinant, sorry. Yes, determinant.
right, so this turns into 1 plus lambda squared minus 4, and I'm doing that rather quickly just because we have two of the same factor, and I'm mentally factoring out a negative sign out of those. So lambda plus 1, or 1 plus lambda squared minus 4. And what are our... So we're going to be 4 away from 1 on either side, and I'm interpreting that. So
close.
Or 2. 2. We have to take the square root. Sorry. So 2 away from 1. So negative. Let's see here. From -1. Sorry. I'm thinking through that. I got there eventually. Okay. So what'll happen is we're going to get a lambda value of 1 or -3. Or 2 away on either side.
Alrighty, sounds good. So lambda is going to be equal to either -3 or +1. Sounds good then?
Which is quasi bad news, because that means that we have one thing that's going to collide with a part of our particular solution. One of the terms in the homogeneous solution, that is.
Right, so basically we just need to note that for later, and we'll come back to it being a problem when we get to it. Alright, now what?
Get some vectors.
Alright, so just as we did in classes past, plug each of those eigenvalues into the matrix that we had up above, A minus lambda I. And so we're going to get a -1 minus -3, -4, -1, -1 minus -3, augmented with 0, 0. Alright, what do we get?
Two, -4, and two in both positions, actually.
Right, since they are the same thing, naturally. And does that hold?
Yes, there. So the x1 is always twice, negative twice. Sorry, x2 is negative twice x1. And I said that awkwardly, but I'm going to stick with it. I'm leaning in.
I'm going to lean into something awkward here as well, so that's all right. So here I'm just going to take negative of row 2 and put it on the top. So we're going to get a 1, negative 2 augmented with 0. And at the bottom, we're going to take what is up there, row 1 and twice row 2, and just add them together to get the bottom row, which is 0, 0, 0.
Right.
Right, and in this particular case, just a reminder to anybody who isn't familiar with this already, we are intending on getting a dependent solution that has at least some number of free variables. So in this particular case, we have one free variable, which allows us to set one of them just equal to t, and say, well, they have a relationship between each other. That's really what we care about. So in this particular case, right, we get... you already said it. 1x1 minus 2x2 is going to be equal to 0. And so x1 is equal to 2x2. And if we let x2 be equal to t, then x1 is going to be 2t.
Yeah.
So we end up with that particular matrix. Come on. We end up with our eigenvector 1 being, again, here we can factor out a t. x2 then has a 1 in its position, and x1 has a 2 in its position. Right, so realistically, again, our eigenvector is just going to be the constant portion of that. We don't need the t out in there. It was just going to be something to help. Okay, next.
Do it again.
Woo. All right, what do we get?
And
this
that one, let's see.
2's are going to be minus 2's.
And this will have the same thing, except now it's just a... you have double x1 is x2, which will just invert the sign of our eigenvector.
Right, so 1, 2, 0, and 0, 0, 0 again. So yep, exact same relationship with just a negative in in place of the other bit here. So C2 is therefore going to be negative 2, 1. All right, how are we feeling?
Feeling good.
Great. Just got to make sure I don't screw anything up. All right, so our X null space solution is going to be what?
C1, 2, 1, e to the negative 3t, plus C2, negative 2, 1, e to the 1, e to the...
All right, so we've got our null space solution. We've got our lambdas that we had before combined with the eigenvectors here, C1 and C2, in the appropriate way. We get all of the little bits that we need. Now what?
Let's make some inspired guesses.
Okay, so X particular is probably going to be of what form?
some vector times t to the minus 3t.
All right, why?
Because when I differentiate t to the minus 3t, I'm going to get some... the product rule is going to kick in, so I'm going to get some e to the minus 3t's that are going to be taken care of by our C1s. And then we're going to get some t to the minus 3t, so getting another, like a... replicating the term that we already got there, and so we're going to get that algebraic equation that we like so much. Which will allow us to solve for the vector A.
Right. So if this t is not present, then we end up with this particular term ending up as a part of the null space solution, which, as we said before, is not going to make it linearly independent. So the e to the negative 3t term just gets absorbed by the c1 to 1 e to the negative 3t term. So we don't want that to happen. We want this to be linearly independent. And in order for that to happen, we then say, okay, let's just bring this up a level in terms of a polynomial order. So here we're going to say that our particular solution includes the t because, as Stucky said, if we take the derivative here, we get some stuff that's got t e to the 3t, if we take the derivative of e to the negative 3t. And we've got stuff that doesn't have the t and just has e to the negative 3t as a part of it. Okay.
If I may, I'd like to insert something physically that's going on too, because like e to the minus 3t is we established that as part of our forcing function. So like that would be like an external impulse or whatever.
That was also something I did not bring up last class, but that is a perfect term that I definitely wanted to bring up.
So I just want to bring this up because so there are 3 rules in DEs that I used to tell students when I taught this class, and the third one was about understanding resonance. And I think this is a part of why resonance is so important, is that when you have a homogeneous steady state solution involving something, and then your forcing function also does that thing, that's going to create a resonance. That you basically have got the frequency of one wave, if you will, or one function matches the other one, so you're going to get exponential, or you're going to get growth behavior. This t term actually has physical meaning because your amplitude is now going to grow without bound of a wave. If you were using a sine or cosine, with e, you're just going to be zooming off to infinity because there's these two things are working in concert. Yeah, there's a fun video we talked about in light of this that I can put on Discord if you like.
The bridge?
No, actually, it's a.
I thought you were going for Tacoma Narrows. Yep.
For the class has some like physical problems. Like there's good reasons to use that example and bad reasons to use that example. So like it's mixed. What I found more effective was getting out. If you know Physics Girl,
Yep.
YouTuber Dinah Cowan, she had a video where she sang at a wine glass.
Yep.
And talked about how she broke the wine glass and did this huge experiments, not huge, but like little mini experiments trying to break it. And the breaking of it happened because she was able to find the natural frequency of the wine glass when you ping it. And she does a wonderful demonstration of this that I think is far more effective than me trying to verbally tell you about it. We watched this in a class I taught one and had fun with it. But the point being that you can, I think this has actually more relevance for the second order DEs for later. But like, this, and I know that's sort of where you're going with this, but I just wanted to point out the resonance part of this. That's another physical reason why you might have the T there.
Yep. So it's perfect in the sense of using the spring example, or as you say, this particular wine glass example. in terms of resonance, and yeah, those are like literally textbook examples of second order differential equations. So we have an acceleration that's happening in terms of a spring. This is something that's going to cause an oscillatory motion. And in the case of the wine glass, it also is oscillatory, but now it's in 3 dimensions, so it's really weird. And let's see, Mythbusters also did an episode on breaking a wine glass with your voice, and they were able to get the slow-mo camera on that one as well. So that was really cool to see. Carrie Byron's voice was in the appropriate range that they found. Some of the other guys tried it. I don't think they were able to make it happen, so they probably left it out of the episode, but yeah, so what I wanted to bring up was we had talked about earlier, Zach, when it was just you and me last class, we said there was another word that's used to describe solutions of differential equations where the dE has no function of the independent variable alone. And so that was when we just had x prime is equal to ax in terms of these vectors. Then we were saying that this is going to be homogeneous solutions. So in terms of physical examples, exactly what you were saying, this is going to be stuff like spring mass examples. There's a whole bunch, but those are the most popular and probably the easiest to demonstrate. There's a couple of others, but anyway. So typically this involves some sort of... I'm not going to go there. Never mind. So typically this involves like a spring mass system or something similar. We have a resonant frequency where if you impart some sort of force onto the natural system, then yes, it will constructively interfere with that particular system. This is the same thing actually that we see in planetary orbit when what is it? Every time that Mars and Jupiter's orbits align, Mars gets a small little kick in its orbital velocity, and it starts picking up motion. Now this is, on a minuscule order, but nonetheless, over millions and billions of years, it will make a difference. And this is also the same thing as what's causing the moon to very slowly start moving away from the Earth. So it's going to be, I think, a few 100,000 more years, and we won't actually have a total solar eclipse anymore. The moon will be too small. Let's see. So this was from 2024-08-05. I posted it in Discord, but at the same time, we didn't really talk about it that much. So the portion, if it had an independent variable alone, this is where we have the g, and that g vector we discussed earlier, and Zach just said it, this is going to be related to a forcing function. Where this is going to be the force that is then imparted on the natural system. So we have the natural resonance, x prime equals ax, and then, that's the homogeneous solution, then we have the inhomogeneous solution, which adds in the forcing function. So what's going to happen eventually to this system? We don't know yet. In this particular case, this would be, if we were to talk about like a real-life application, this one's going to be a little awkward just because it's a first-order system, and so this is like our pond example, which is probably not going to go terribly well, but nonetheless. We have some sort of essentially like spillover of the pollutants that were in each of the ponds, and they each have some sort of inlet that has a certain concentration of pollutant that's coming into the water, and then both of them have some sort of system by which the water is going to leave the system, taking some of the pollutant with it. So in this particular case, if we're looking at a forcing function for this, this is going to be the amount of pollutant that's coming into the system just by itself, or out of the system by itself, depending on how exactly we're looking on it. Might be a little convoluted for this particular one, but again, once we get into the like spring mass systems and the second order differential equations, I think it'll make a lot more sense.
Honestly, Obi, I think that Laplace transforms were more convoluted.
That's fair.
Ooh.
Only another month or so.
I'm being cheeky and a little bit, anticipatory, but I mean, those who know.
Yep. They can get a little spicy sometimes. Okay, so we've got our x particular for this one. We said it's got to be linearly independent from the natural part of the system, the null space solution, or the homogeneous solution. So we have to then impart this t as a part of that, so it's going to then be linearly independent. Then we also said this needs a b vector with e to the 4t, which is going to be the other portion of our non-homogeneous portion. So our g vector from up top had an e to the 4t in it. And again, the solution is going to have some vector which has e to the 4t. We don't know exactly what it is, but we'll get it. Okay, now what?
Plug it in and see what happens.
All right, so x particular prime is going to be equal to a times x particular plus our g vector is the system. And then we said here, when we did this as a total system, which included both the null space and the particular system, what happened?
The null space one is going to cancel.
Right. So because these were linear operators, our null space solution ends up separating out from the rest of them, and then it's just the stuff on the left is equal to the stuff on the right. We have both of the null space solution parts, which we said up top, they are equal to each other from the null space. And so that drops out entirely, and we can just focus on the particular solution here. We don't have to deal with the null space solution as a part of the overall system. Okay. So what is x particular prime? Oh, yep, you got it.
Oh, no, sorry, I was just writing out the...
Okay. All right, so left-hand side, we're going to take derivatives. Again, in this case, e to the negative 3t, easy enough to bring that down. So that's going to be a negative 3 times c1 times 2 up in the top row. So a negative 6 c1 e to the negative 3t. And second one is just going to be e to the t again. So we get a minus 2c2 e to the t. And second row, again, negative 3 times 1 is going to be negative 3 c1 e to the negative 3t. Plus e to the t is just by itself here, so c2 e to the t. All right, got our left-hand side.
Sorry, should the C's...
Yeah, no, that is totally not. I just did the null space solution, so that's cool.
Ah, I see.
There should not be C1 and C2. It should be A and B. Apologies. All right, cool. Right, so this line, take the derivative, and in the top row we're going to get our A1 times, again here if we take the derivative of t first, we just get left with e to the negative 3t. If we take the derivative of e to the negative 3t, we end up with a negative 3 a1 times t e to the negative 3t. Right, and then if we take the derivative of b e to the 4t, we're going to get a positive 4b1 e to the 4t. Second row, very similarly, just going to end up with a2 and b2 in those particular places. Nothing else is going to change. Please tell me if I'm wrong.
Now, I'm wondering if we need an extra term in
What's that?
well, I guess maybe not. I was thinking about the particular being needing to include a c vector e to the minus 3t. If that needs, I don't know if we need that though. Now that I'm thinking about it, just so that we have the extra, what's it called? The extra. Oh, can't even think of the degree of freedom. That's what I mean. To control that constant.
Right, so normally I would say absolutely, if you're going to start with a particular degree of a polynomial, then you need to follow that polynomial all the way down. So why wouldn't we do that here?
I guess if we know the hyperhomogeneous, it's fine. But I guess let me think. Why would we want to do that here? Yeah, the C1. Yeah, I guess that's true.
Yeah, so since
Because
we
you
already
have the C1
have
there.
Right, since we already have the null space solution which has that same term in it. So it's going to be 2 times
So that would
C1.
be redundant. Yeah.
Yep.
Okay. I'm with you.
Yep. So if it just happened to be like, if our null space solution ended up being like negative e to the negative 5t and e to the t as our fundamental set, and then our particular solution had t squared e to the negative 3t. So we would start with t squared and then work down to t and then work down to constant, because if we take the derivative of this thing, it can be any of those things. It can have any of those individual terms. So we do want to include those. The only reason that we're not doing it here and saying, okay, it's going to be, a times t e to the negative 3t and c times e to the negative 3t is because we already have a c times e to the negative 3t as part of the null space. So yes, thank you for talking that out.
I'm grateful I did. Thank you. This isn't a procedure I run every day, so I'm trying to think of it. I'm trying to remember all the little details here. But if I remember correctly, that makes I'm fine with it. Yeah.
Yep.
Satisfied.
And I mean that's something that you would always said in real analysis is like, even if you suddenly think you're wrong, or if you just think of something like a student out there might think of, it's going to be an important process to just talk that through no matter what.
Agreed. Yeah.
Zach, let me know how you feel about this so far.
I think we're okay.
Okay.
I got to get in the habit of keeping this thing on, keeping an open mic, a hot mic instead of a muted one. But I was saying things and I'm realizing, oh wait, you're not here. So
I do enjoy
yeah,
my boom mic being here that I can just flick out of the way, and when I do that, it turns it off automatically.
That is nice, yeah.
I want to get like the sports broadcaster thing where you can have the little switch that can literally toggle.
Yep.
Or do like a stream deck or something, you know?
Yeah, I'm pondering getting a cough switch.
Yep.
Everybody who has been here longer than 2 minutes is probably saying yes, please. All right, how we doing?
By the way, I posted the resonance video. If you're interested, it's in the math chat. You don't have to watch it now, but like I was thinking about like if you before I forget about posting it. Sometimes I'll say I need to go post something and I never do it. So that's my bad, and I'm just gonna. It's there if you want it, but
Awesome.
it's a fun little watch. She hams it up a bit, but it's fine.
And these days we need a Diana fix because she's off.
Well, and I subtly I want to give her the shout out because of what's going on for her personally. I just know so many things are difficult for her right now.
Yep. So for anybody who doesn't know, Physics Girl was on YouTube for years. I mean, and became kind of a fixture of the science community.
It partnered with PBS pretty often, and
science communication community, however we want to say that. And she did some really great videos. This is, I mean, just one of them. But her, she ended up catching long COVID and has been essentially bedridden since that point. Her husband quit his job in order to take care of her full time. They've had one or several care nurses in and out to make sure that she's getting, they both are getting what they need. And so it would be helpful if anybody has any extra funds that you might be interested in sending their way to make sure that she's getting the care she needs, whatnot, and that'd be helpful. You can just go to her YouTube page at Physics Girl and find her that way. They've been doing reruns. The people who have been managing her channel have been doing reruns a lot, so that does help as well. Even your views are helpful. Don't want to be too awkward, but All right, how we doing?
I think it's time to do some much dreaded simplification, huh? I know, right? So I think what happens here is we just take we'll have 6 equations to solve, which is somewhat painful. So we'd have a minus 3a1 equals the minus 4a. Sorry, minus a1 minus 4a2. I mean, I was going to suppress that part of it, but now that we're on the subject, so I think it might be strategic to put these in. What am I trying to say? To just take the A terms and solve for those first, and just look at the different pairs. But this will basically amount to solving systems of equations, several pairs of them.
Right. So what we're going to be looking at is try to get all of the terms which have exactly the same variables, and just saying, look, those things are going to be equal to each other, and therefore we can for all t values, right? So we can ignore them and say, look, for all t values, our coefficients must be the same. Otherwise, the functions themselves are going to be different in some way, shape, or form. Yep. Ah.
I'm just trying to figure
Oh,
out what
no,
we're
that's okay.
working on. Yeah.
I got it. I was confused there for a second because our a1 e to the negative 3t does not appear to have anything in the first row that corresponds with it.
Right.
But that's actually good. In this particular case, if we look at the particular portion, our g vector, there is no e to the negative 3t in the top row for the g vector. So naturally, our forcing function can have a 0 in the first row for that one. So that does simplify things by itself pretty nicely. a1 e to the negative 3t is going to have to be equal to 0, and therefore a1 has to be equal to 0.
Then that forces A2 to be 0, which concerns me. That's where
Yeah,
that's
okay.
why I was thinking, well, maybe we need to go back to what I said earlier. Why I'm bringing it up, I was like, well, maybe we still need it. But
Touche. Yeah, we might actually need it. Cool.
And this is one of those things that I think is useful to show anyway. The fact that this mistake happened, right? Like, I mean, in some ways that emphasizes the need of what kind of solution we choose. That it can't just be like we normally do, where we say a t to the t e to the minus 3t. We have to include the other constant term as well because there's that degree of freedom problem that we're running into right now.
Yep.
We don't want to couple unnecessarily those solutions together.
Alright, so we'll add a d1, d2 in there with e to the negative 3t for both. Which then means, what does that change? That changes the right-hand side.
Oh, I see. Yeah.
Changes the right-hand side of this one. E to the negative 3t. This is going to be then a negative d1 minus 4d2. Yay.
What do we want? All the variables. When do we want them? I don't know.
Okay, so we can get a 1 in terms of d.
Let's start thinking about these.
So yeah, the D's now get thrown in as well. The
Okay.
Use my sticky terms here.
I think I want to do a row reduced echelon form of a matrix. Let's probably make it a little bit easier. At least I certainly hope so.
I mean, this is. I know you're going to be getting to this point, but variation of parameters is slightly more effective here, I think. Personally,
quite possibly.
Yeah.
So this is going to be negative 2a1 plus 4a2 0.
Yeah, sorry, Obi, I'm working on that.
So are you thinking we're going to make a system of equations out of just all this stuff and make a matrix?
That's what it's looking like. The thing that I have created at the moment is a 6x9 matrix. Which doesn't seem... I'm missing some terms, I must be, but...
I don't know if you can share that matrix so we can sort of see it.
Woo!
I don't know. There. Oh, it's on your TI.
Yeah, I haven't done anything with it at the moment, but...
Okay.
So my intent, right, and let me just write it down. So my intent was that we get all of our different equations set up so that we have A1, A2, B1, B2, C. Oops, we're not doing C. Ah, there was my mistake. D1, D2. Oops, that's a little close. Augmented with whatever constants we have for those equations. So we have 6 variables, and we should have, as Stucky said, 6 equations to work with, which are all going to be equal to the things that are on the left-hand side individually. So the 3 up top, the 3 down bottom. So this makes a 6x7 matrix much better. So with the first couple here that I wrote, we get a 1, 0, 0, 0, 1, 4, 0. Negative 2, 4, and all zeros. Right, I mean, Stucky's is probably more efficient because it's just like one at a time. Yep, I totally forgot the 21 to the 14 there as well. T, -3t, we get A. 1, -2. Well, I'm not liking the fact that two of these are linearly dependent. A row here and a row here.
That might be okay. Because
That's part of our
we
null
might-
space?
yeah,
Okay.
yeah.
Cool.
Those correspond to A1 and A2, which
Yeah.
is like we were saying earlier. But it's good to verify. Definitely the D's are going to be important.
Right.
Although, I am concerned about that. Because that means that t e to the minus t is not, or minus 3t is not a part of the solution space, which is odd. It should be there.
No, it is. It's still, it's 2-1 times t the minus 3t. That's what.
Oh, I see. Gotcha. Okay. And the 2-1 came from our null space, right? The null solution? Or I
Maybe
guess...
I just got it by looking at the second row of this matrix. But perhaps for theoretical reasons it should be.
Oh, I see what you're saying. Got you. Okay, so you're saying... Right. Sorry, my bad. I think I'm... I had to actually process what that means, but negative 2a1 4a2, we can choose to be anything, so we'll just choose, any vector scalar multiple of 1. What would you say? 2, 1? Or 1,
Yeah.
2?
2-1, yeah.
2, 1. Okay. Cool.
Got the row reduced form on the bottom left. Which means A1 plus D1 is 32/3. A2 plus D1 is 16/3. B1 is 5. B2 is -1. And D2 is -8/3. Nope. Wrong ad. Grr. Alright, we're back.
Alright.
Sorry for that, everybody. I didn't get a notification.
Okay. I don't know what happened, but you are here.
Yep. It was an ad break.
Uh,
Involuntary because I didn't do it myself. Okay, so from above we have that a vector is our t e to the -3t. And we can let a1 be in terms of d. T. So this is going to be 32/3 minus d1 and 16/3 minus d2. By rearranging stuff, also going to want to put d vector next to this one, just so that we can see exactly what's going on with it. E to the -3t, and our d vector was just going to be d1. We don't know what it is, but it's related to our a vector over there. I don't know if it's wiser to have it the other way around, but it's fine. D2 was -8/3. And our B vector times e to the 4t was 5 -1. All right, since A is in terms of, this is, Any thoughts in terms of what we do here?
I'd like to set d1 equal to 0.
That's fair.
I mean, when in doubt, choose the convenient choice, right?
Yeah, well, I was like, oh, we could let it be t, but no, that's a terrible idea because it'd be t squared in this term, so that doesn't, yeah. Right, so, that'll be fine. I don't like fractions on the inside of this. Let's do 16/3 on the outside. Which then makes it 2/1 times t e to the negative 3t. Plus, this is going to be, again, let's just do 1/3 here, makes this a 0, -8 e to the negative 3t, but this is going to be absorbed as part of our null space.
No, that's not true.
Okay. Is it because the vector is not the same?
Right, so the vector's not the same.
Okay. Well, thank you for pushing back on that. And in theory, at this point, we could, like, combine this into one term and have our, like, t's and constants on the inside of the vector, but I prefer not to. I would just as soon leave everything just as is in place here. Plus our 5 -1 e to the 4t. Alrighty. How we doing?
Well enough.
I think this process gets pretty long pretty fast. And I remember I had a class as part of grad school that we did problems like this, and they tended to take a lot of diagnosing like we're doing now.
Oh no, what went wrong? Yeah.
Right, no, and a lot of the times it's just keeping track of everything.
No, that's just e to the t. And then plus... all that stuff we found down here. Everybody's favorite trick, let's just copy paste. And let's also switch colors. Oops. All right. So there is our X solution for this particular system of equations, including the non-homogeneous portion. All right. Other comments? Questions? Feel free in chat. Anybody who's wants a little more clarification on this, we're happy to explain. Alright, let's take a look at the next question while we're at it. Okay, what if the inhomogeneous portion to the differential equation contains a function that is not part of our usual set of functions, like a tangent? So for instance, we had looked at what happens if our inhomogeneous portion contains a sine function. What do we need to add as part of our inhomogeneous solution portion?
Sines and cosines.
All right, why sines and cosines?
When you differentiate sines, you get cosines. So if you have a sine term, then you need cosine terms potentially to cancel it out. And we get lucky because when you differentiate cosines, you get sines, and we already have sine terms, so that's accounted for.
Right, so like we had with our, we had seen in the, inhomogeneous portion for the last one, we had t e to the negative 3t for the same reason. So when we take the derivative of either the t portion or the e to the negative 3t portion, we need things in order to cancel other stuff out, so that when we, on the right-hand side, just multiply this particular thing by a constant matrix, we're going to end up with the same stuff there as we get on the other side when we differentiate. In the correct proportions and all that.
Well, and that's the advantage here with sine and cosine, is they have closed derivatives. E also has a closed derivative, in a sense, up to a constant. Tangent, you could maybe argue that has some properties, like with secant. You could argue that there's some things you could do there, but they're not as predictable as sine and cosine. They don't have just constant multiples. You end up getting powers of tangent and secant, and you don't have the nice closure.
Right, and then we take the derivative potentially of secant, and it ends up being, another, secant 2 secant times secant tangent. So we end up with secant squared times another tangent. So like, how does this interplay actually work? So this is where it becomes a little awkward.
Sure. And so we can't just have a constant multiple, like having it, that constant multiple doesn't exist. We're multiplying by secant and tangent, so there's some sense of closure, but not in the same way that sine and cosine have this constant multiple property. But we can do the next best thing, which is to integrate.
Which part?
Well, I mean, we'll be able to integrate with, maybe using an integration technique would be helpful to, in the spirit of what we did back with integration factors.
Right, so is there some sort of way that we can entangle functions, if you will, in order to make these come out much nicer? Really? Come on, man. Just decides to do nothing. That's weird. Alright. So, let's let our... All right?
Yeah.
Okay. Let's let our x sub p vector exist as a product x of the fundamental set matrix created by, in this case, taking our null space solution and then just concatenating all of our solution matrices together. Now, keep in mind, this is kind of what we were doing last time when we were diagonalizing the matrix, where we were looking at taking the eigenvectors and concatenating them together. So we're just taking all of them in any order, by the way, right? And just sticking them next to each other as columns of a particular matrix. In this particular case, we're doing the same thing, but instead of the eigenvectors by themselves, it's going to be the kinds of functions that we're using for all of our solutions. So, in our null space vector we had here, we're going to use the constants as part of our eigenvectors as well. And we're going to say that our fundamental set that we're going to use for this is going to be 2e to the negative 3t, negative 2e to the t, and then underneath e to the negative 3t, e to the t. And then multiply that by u, which is going to be a dummy variable vector. So we're just saying, like, it's sort of the same, again, like I said, for our diagonalization of matrices. We're, instead of taking t and multiplying by y, some other fake variable that we're using for a few moments. Harbor of Memories wrote an equation. Can you help me? Maybe. So we are currently in the middle of a differential equations class. Choose times k factorial. Interesting. Okay. I may have to think about that for a while. Okay, so we're going to let our x sub p vector, our particular solution, be this capital X vector times u, which is, again, going to be a dummy variable for us, which has exactly the same size as our particular vector x sub p. And then we want to figure out how can we solve for u in order to then be able to back ourselves up again and say we're going to get the inhomogeneous solutions, or the particular solution, x sub p. So in this particular case, we had 2e to the negative 3t, and underneath it, e to the negative 3t. Over on the other side, negative 2e to the t, and e to the t, as their two columns. Right, and then we said here, this is going to be u sub 1, u sub 2. And again, this is going to be our x sub p particular solution. And so when we try to solve this, what do we need to do?
Solve this. Differentiate?
Because we're plugging it in
to the original differential equation.
right, yeah. So we're plugging it into our original differential equation with the g forcing function on the end, or f. Yeah, sorry, we called it g. And so we're going to plug all of that in. Harbor, we're using... sorry. Woo. We're trying to work out what exactly is this whole variation of parameters thing for differential equations in first-order systems of differential equations. So... I'm also doing this kind of from a position where we don't know what variation of parameters is for any other kinds of differential equations. So we're trying to come up with this just from from its own standpoint, essentially. Right, so we let our x sub p prime be equal to a times x p plus g vector. And then in this particular case, we're substituting in our x times u into all these pieces. Righto. Alright. Let me pull that over there. Nobody saw it, it's fine. Sorry, I got distracted from my particular notes here. So, there we go. And this is kind of where things will go really sideways if you mess anything up, so I wanted to be pretty careful with it. Apologies, everybody. Okay. Left-hand side, what do we end up getting?
I guess x prime u plus xu prime. Just said that, but seems believable.
Right, so it wasn't the case when we had a T matrix that we needed to differentiate T. Why is that?
It wasn't T a constant matrix?
Yeah, it was just made up of our eigenvectors. So in this case, we're like, well, these aren't eigenvectors anymore. Now they're including the fundamental set of functions as well. So because it's also a function of T, we need to differentiate both parts, and since it's multiplied together, our matrices act more or less the same way as just regular functions of T as well. So yeah, we need to multiply them together using the same product rule that we had for Calc 1. Alright, and on the right hand side we've got AXU plus G vector. Stuki, what do you notice?
Those first terms are the same.
Which ones?
The first terms on both sides of the equal sign.
So our x prime u
Yeah.
and ax u.
Am I right? Okay.
Because?
Yeah, those. Because x is defined. Well, the columns of x are solutions to the differential equation. So if we look at each of the columns, well, we're taking a u linear combination of of solutions to that differential equation, or to the homogeneous differential equation,
Mm-hmm.
which is again a solution to the homogeneous differential equation.
Right. So in this case, what we can say is, well, if these things are the same, we can subtract them off just the same as we did in all the rest of it, or we can take out the other two things which are in the equation and set them equal to each other, being equivalent in either way you explain it. So here we have x times u prime is going to be equal to our g vector. So x prime is going to then, x particular will be a solution, x, capital X times u, if and only if we also know that x times u prime is going to be equal to g. So we're going to be able to find a particular solution, and we're going to need to solve this equation for u prime much in the same way that we solved our original, or tried to solve our original equations for x prime, and then eventually we can solve individual equations. So for this one, let me bring back x there. Covered it, of course. Okay, so x is going to be 2 e to the negative 3t, negative 2 e to the t, e to the negative 3t. Wow, okay. And e to the t multiplied by u1, u2 prime all right. Scaladraw is just trolling me at this point. All right, must be prime, must be equal to, now we get our g, which was 21 e to the, is it negative 3t? Or was that, no, that was on the bottom. 21 e to the 4t and 8. E to the negative 3t. All right, where do we go from here?
Inverse matrices.
Sounds like it. So yep.
So this would be done the same way as before. Like you'd find a determinant, and you could swap diagonal entries, or swap the signs on the, what is it, the minor diagonal, diagonal.
Yeah, I
swap
always mess
the
that
actual
up.
entries. I think that's how it works.
Yeah.
I do like this. I've not seen it written this way before, but I like the use of the product rule, which is consistent with what you see in first order equations, for instance.
Yep. And also the matrix multiplication stuff that we're doing here is at least, not the same, but very similar to the diagonalization that we talked about last class. So it helps kind of tie all these individual threads together, so that finally we can get like a whole, much larger picture. All right, so x1 is going to be x inverse. Jeez.
Well, so
Sorry.
I guess we can first write out a 1 over e to the minus 2t, because that term will be part of the inverse, since that's the determinant of our original matrix.
Okay.
And I need to verify it'll be a 4. Be 4 e to the minus 2t.
That's right. Right. Minus e to the negative 3t and times a negative 2e to the t. Okay. And also super important, right? What was the determinant not?
Not 0.
Yeah.
I mean, it can't be unless you have, in this case, the only time that could happen is if your e to the minus 2t were 0, which shouldn't ever, in practice, happen.
Yep.
I say that in practice because in principle, if t is infinity, well, there you go.
I think we can assume that at least we're going to get finite values of t in standard differential equations.
Yeah.
Okay, and yeah, one more time with these. We said it was swap main diagonal.
That's right. So swap the main diagonal and then change the sign of the other.
Okay, and multiply by g. 21e to the 4t and 8e to the negative 3t. So u1, u2 prime should end up with a matrix solution. 1 over 4e to the negative 2t. And here we get a 2 by 1 matrix, which is going to be e to the 5t times 21. Okay, and plus 16 e to the negative 2t. Second part, we get a negative 21 e to the t. And a plus 16 e to the negative 6t.
And then just divide everything by 4 and e to the 2 minus 2t. We should be all right.
Let's see, so we got 21 fourths e to the 7t plus 4e. Nope, that's gone. Plus 4. All right, and bottom negative 21 fourths e to the 3t plus we're going to get a 4 e to the negative 4t. All right, how are we feeling?
Okay.
And that is our u prime.
Which you could then integrate
Right, because these are...
These are solutions to, like, they're just differential equations.
Yep, so if we go
Literally
back to
ones.
our original, vocabulary from way back at the beginning of the semester, from the beginning of the year here, we've got equations that are first order, linear, and separable. So, very nice, very simple comparatively to solve. And granted, this is only an intermediate step to get back to our actual answer, but good enough for now. It's at least getting us somewhere. So negative 21 fourths e to the 3t. Zach, you also had said that this was likening this process to finding what?
The integrating factor. And solving first order equations using integrating factors.
Yeah. So I think I had kind of maybe been a little bit dismissive when you said it the first time because my mind was somewhere completely different. But yes, I processed that, so thank you very much. All right, so u1, we take the we take the antiderivative of everything that's here. We can also say, like, this is again du is equal to this stuff dt if we really wanted to take the integral of both sides, what have you. So we end up with, this is going to be 21 fourths. We divide by 7, or take the 7 that's already part of 21 and absorb it into the dt for that term. So we end up with a 3 fourths e to the 7t plus 4t. And u2. Also, what did I forget? Quote unquote.
The plus C?
Right?
Or the... Yeah.
Yeah, so normally when you do integration, you want to add a plus C to all of the endings of this. Why do we not care in this particular case?
Just because we're looking for a particular solution, so anything's good enough. Plan.
Also true. What's going to happen to that C term, or in fact C vector, because it's in both of our equations, if we then go back a step and say, okay, we've got our u1, we've got our u2, what's next?
Multiply that through by x.
Mm-hmm. And if we multiply each of the individual terms by our x, well, not individual, but if we multiply our x matrix by the constants that come out of the integration, what do we end up getting? It's a term that's all...
That's all in the null space. That's all
right.
in the homogeneous.
So that is going to end up being in our null space. Now I can finally say that correctly. Because all of that was going to be our constants times our fundamental set. Well, if it's a fundamental set of solutions, just times a constant, then it's going to end up coming out to be the same as our null space, or within the null space. Alrighty. So here we want our x times u vector, which is then going to be, again, 2e to the negative 3t, negative 2 e to the t, e to the negative 3t, and e to the t. Multiplied by ru, 3/4 e to the 7t plus 4t, negative 7/4 e to the 3t minus e to the negative 4t. Which is then going to be equal to
Oh goodness, gotta go and add everything up.
yeah.
Well, so conveniently, I think these will combine into one anyway. We'll have we'll have 3 halves e to the 4t plus 8t e to the minus 3t.
So I think we're going to run into the same thing that Zach, you and I did yesterday, where if we had separated these out into 2 separate things and then done them as distribution, then this makes it a little bit easier. And really, if you want to do it now, it's just a matter of organization within your head, right? So if we multiply our first row by the first half of the first column, then both of those terms end up with e to the 4t, and so that's kind of nice.
Right.
So we end up with a 3 halves plus 7 halves e to the, again, 4t. And then first row, second half of the second column ends up being a plus 8t e to the negative 3t. And bottom one is a positive 2 e to the negative 3t. Alright, same deal for the next one. So 3/4 minus 7/4 e to the 4t. Plus, here is a 4t e to the negative 3t, and a negative 1 e to the negative 3t. So if we look at this stuff, let's see, this combines to be a 8 4 t e to the negative 3t plus a 2 negative 1 e to the negative 3t and a, it's going to be 10 halves is 5, and negative 4 over 4 is negative 1. E to the 4t. X particular. What do we think?
Neato burrito.
Right, because our original that we had over here look a little bit different, but did I forget anything else? Always possible.
So this is sort of interesting that I'm as I'm looking at this, like I say, I'm not used to seeing variation of parameters this way. Systems done basically using a process, which is I find fascinating as a new learning, if you will. Or just seeing it this way is useful. So often I resort back to some of the formulas you see with integrals and
Yep.
multiplying matrices and so on, and I think that almost is meaningless. And I think this offers some meaning that is consistent with previous learnings, right? You're not breaking any rules. No previous rules were broken. The same product rule is applying here, which is sort of nice.
And it's also not standing up on stage and saying, here's a formula you need to memorize. Which
I like this method. That's sort of it's sort of nice.
Yeah.
Alrighty. Yeah. Any idea why those things might not be the same? Because that's something that does bother me. We do at least get these to be the same, so we know that that's probably 100% correct. There's something going on with our te to the negative 3t term that is not sitting right.
What is comforting, if it's any consolation, is that 8, 4, and 2, 1 are scalar multiples of each other.
True.
So that is sort of comforting to me, that you could find a C value of 4, and this would make the at least e to the well, hold on.
Yep. There's also the 1/3 to
like
contend with there.
Right, but I'm noticing that these are the eigenvectors that we were getting before, which is comforting.
Mm-hmm.
That to me at least gives me some hope that we're doing something right. Without like actually going to, I remember there was somebody on stream who were doing one of these, and the person actually came back several times and said, "Let's actually finish this problem." And it was sort of a nightmare to go through. I don't know if anybody was watching the stream at that point, but this was a few months ago. And I remember just there's a lot of diagnosing I think I'd have to do to really pin down why these are different.
Yeah.
It just seems to be par for the course for these kind of problems.
Right. And I mean, if I had to guess, I would probably say that there was an issue with maybe somewhere in here I messed up an equation. I know for one of them I definitely dropped the 21 first and then added that back in. So it's possible that I miscopied something in here. If so, that's a little frustrating. But also, like, the, let d1 be 0. Is there a d value which could make this work? Well, that should be an easy check, I think. We want it to be 2, -1. So if d1 were 16/3, I think that could potentially work. Let me just put a star on that and I'll do that later. Okay. All right. Anybody have any questions, comments, concerns? Apart from that. Okay. So next class on Monday, we are going to be talking about what happens when we have nonlinear systems of differential equations, and then how do we... I don't want to say fix because that sounds mean, but how do we deal with the fact that these are nonlinear systems of differential equations, and a lot of the times we can't do anything with them. It's like, what are some ways we can at least analyze the system and come up with a reasonable approximation of this incredibly potentially large / chaotic system of nonlinear differential equations. So, if anybody wants to plug anything, any cool projects coming up or anything like that, you can let the audience know.
I will be coming back to stream later this week, probably Friday. That'll be announced over in the Elements. But yeah.
Awesome. Can't wait to see it.
Sounds great. I was going to say, yeah, that's awesome.
Zach, anything for you?
You know Infinite Series. That's about all I got.
Yep.
Just a lot of my times I'm doing that in my my what's it called? My dissertation.
There's a word for it.
That's a word. I was gonna say it's something that's important, and it starts with a D.
It's the D vector.
Yeah, well, it's become the D word in some ways. Yeah. Actually, one of my kids was saying something about they'd mispronounced dissertation. It was more just funny that they had to correct them on spelling. I'm like, okay, hold on, that's not exactly what that means. Good times though.
As long as your dissertation is not becoming a diss track of mathematics.
Well, and honestly though, like I've said, it's all been just writing. And that's all I have left. Like literally, I have no other ties to the university other than this dissertation. So,
yep. Woo.
So anyway, yeah, I'm looking forward to December. Presumably, that's my target date.
Nice.
So I'm hoping that's and we'll. I mentioned yesterday on stream that I'll probably have I'm gonna try to see if we can get it a live stream of the dissertation. If I can pull it off, I'd like to put it on Twitch. That'd be sort of unique. I haven't seen anyone do that.
Live defense?
That'll be sort of interesting. I like I said, I don't know anybody who does that regularly. Sort of a one-time only deal. So we'll see if I can pull that off. And I think I can. I have an angle in which I might be able to. So we'll see.
If it were me, I don't know if I'd want everybody seeing me sweat so bad.
We'll see about it. I mean, there's lots of questions. You'll probably get a minimum. We'll put out as so it'll be fine.
Alrighty. Well,
thanks
thank you
so much.
both. Yep. And we'll be back on Monday for Differential Equations, Part 11, Linearization of Nonlinear Systems.
Cool.
Alrighty.
Well, GG's, everybody. And thanks, Dookie.
Yep. Thank you both for hanging around. And we'll see you on your streams as well. Alrighty. We are going to continue just a little bit for the rest of the night. We'll disconnect from Discord here. Yep. And we'll decide what we want to do. So, I guess first thing, Harbor of Memories. This was a way to prove mathematically that there can be more narrative permutations than there are atoms in the universe. Is this having to do with the Noam Chomsky debate that was happening on Twitter? Somebody had said that they had reread Noam Chomsky, and like his earliest book was just like constantly insisting that there were going to be an infinite number of permutations of a finite language system. And this person was like, how can this even be possible? And it boiled down to infinity's weird. But it was just kind of like, you know, I and every other person who understands math/infinity being like, well, yes, you can literally just say, this is the number 1, this is the number 2, and continue on forever with numbers, and that's all. So you can have an infinite number of ways in which you are just describing numbers. So therefore, there is an infinite way to describe what is it? There was an infinite set of sentences that could be created. And that was the main thrust of it. But yeah, person's like, I just don't understand. And we're like, it's infinity. It's weird. Like, if you're not a mathematician, if you don't think about these things for, on a regular basis, then of course it's weird. Chikiro, thank you very much for the follow. That's also weird. Why didn't that go off? There was supposed to be an alert. Do we not have... Well, Stream Elements is up. Okay, well, that's weird. Let's run a 3-minute ad, clear stuff for the next hour, so nobody has to have any pre-roll or mid-roll ads, and then we are going to continue this discussion that we had here about what happens if we let D1 be 16/3 like we had planned over here. Can we then recreate the other that way? Can we recreate the other terms of the particular solution which came out from the other one? And then, right, would we be able to figure that part out, like, without any of this stuff? I think the key there is to ensure that this eigenvector is 2, 1. No, well, it's always going to be that. Or is it? Wait, hang on. No, because we're subtracting. So if we subtract the same amount, we should be changing stuff. Oh no. If it's 16/3, that one's going to be 0. Ugh. Man, this is screwing everything up. How do we get... I don't think we can get 8/4 if we do that. I mean, just looking at it, right? Like, we can't get... My hair's sticking up, that's annoying. We need to get 48 in the top. So it'd have to be a negative 16/3. And a negative 32/3, which is still not twice the amount of the other one. That's going to annoy me. Okay. Yeah, I don't think it's going to work. I think there must be an error somewhere. Oh well. Alright, let's take a 3-minute ad break, and then we'll discuss more about that. So, everybody stretch, go get some water, cycle out water if you need to, and we'll be back shortly with more math stuff. Thank you everybody for coming. My name is Obi-Wan Pez, this is N-Simplex Pachinko, and 3 minutes. And we're back. If anybody has any particular questions that they would like to ask about mathematics, about education, about anything you feel like, please let me know. We also have a community that we have here on Twitch. These are the Math Chads. Our list currently stands at Dawn Does Math, Zach, who was just here, e to the 2i pi, Penn Center, enstucky, who was also just here, myself, Obi, at nsimplex pachinko, Danny Highway, and Dr. Gold at Actual Education. Any of us are lovingly referring to ourselves as the Twitch Math Department. Members of the Twitch Math Department. We are also intending on all of us to be members of the Knowledge Fellowship, that is TKF. I don't think we have a... No, we don't. The Knowledge Fellowship is a group of streamers who are interested in doing educational content in our particular specialties and expanding out, trying to do some cool stuff in terms of educational content on Twitch. So, we also have a TKF Discord. Yeah, that's... I don't have that because that's probably also on... It's probably also on Stream Elements. That's really awkward. It's not working. But at any rate, last time I tried to post TKF stuff, they did not work. So, I can attempt it. But no guarantees on this one. So, if you're able to, this should be the Discord invite for the Knowledge Fellowship, TKF. And if anybody feels like joining in, it is for both educational live streamers and viewers who are interested in educational live streams. So many of the other really cool people that we have... Let me just double check here. Yeah, okay. Nice, yes. So I see Zach and I are on the list now for mathematics and economics. So anyway, yeah, so we have some other really cool streamers who are on there. Is it 1999 because I'm watching a Matrix? Yeah. That was... That might have been the first rated R movie that I went to the movie theater with my parents. Certainly after I turned 17 and just could have gone myself. But yeah, we walked out of there and we just had our minds absolutely blown. It was 3 of us. It was me, my mom, and my brother. My dad was at work, and I think it was over summer holiday, I want to say. So, you know, Mom was just trying to get us out of the house, essentially. That can't be right. Hang on. Nah, Dad was working, but at any rate, she'd heard great things about it and was just like, I'm taking you to go. My brother was 14 at the time, so he definitely needed a parent. And then my mom was just like, I'm going to pay for you, so you can go on your own if you want. How's it going, Silver? Yeah, so this is... I was just thinking about this. This is the birthday problem. The issue that we have is that we were saying let d1 be equal to 0 in order to set our first eigenvector, essentially, to be the 2, 1 that we wanted over here. And, you know, d1 being 0 is just much easier, so let's do that. The problem is that if we do that, then we get these funky sorts of looking constants and things like that all attached to this. And when we go to our like other solution that we found using, matrix multiplication, we end up with 4 times the vector 2, 1, t e to the negative 3t, plus 2, negative 1, e to the negative 3t. But we're not getting that over here. And if we try to change one of these vectors, right, the other one is going to necessarily change as well. Because this is what I was saying, it's the birthday problem, in that you only ever once reach a multiple of somebody else's birthday, or a percentage of somebody else's birthday, if you are staying the same distance apart the entire way through your lives. Ready to chill? Nice. Well, I hope it is a wonderful chill. So the only time that we ever end up in a 2-to-1 ratio is going to be if d1 is 0. And then that's going to give us this multiple on the outside of 16/3. Whereas in the other one, we had a nice constant multiple of 4. So we're off by a factor of 4/3. And then the e to the negative 3t here, like, we shouldn't really have that in the first place. I know I said that it should be absorbed in the null space solution, but at the same time it's not going to be, because it doesn't have the same eigenvector in front of it. So if we force the eigenvector to be the same, by saying this should be 2, negative 1, e to the negative 3t, right? 2 to 1 is going to be that, or 2 to negative 1, means that d1 should be 16/3. But if d1 is 16/3, then over in this matrix, we end up with 32/3 minus 16/3 is 16/3. And then 16/3 minus 16/3 is 0. Right? And then if we make it like negative 16/3, well, that's just going to mess everything up, because then the eigenvector is not going to be the same in the middle for d, and then the a vector is not going to be the same in a 2-to-1 ratio. It's going to be a 2 to 3, 3 to 2 ratio. So, like, man. Alright, we'd have a 16/3 out front would be a 1, 0 matrix times t e to the negative 3t. Whereas, you know, that's probably fine. It's not true. Right, we found it a different way, and it's completely different. Our null space solution that we found earlier has e to the negative 3t, 2, 1, e to the negative 3t. This is 2, negative 1, e to the negative 3t. So even that's wrong, right? Okay, how about we make this 2 to 1, right? Then make it negative 16/3. Well, we just talked about that. It gets this one in a weird ratio as well. So So I don't know exactly what we're doing here. Like I said, I must have messed up these equations somehow in here. There's probably an easier way to do this other than what I definitely forced Stuki into. In terms of like getting just all of this stuff. It's messed up, man. So if anybody is interested in giving me any math problems, stuff to look at, stuff to work on here, feel free. I am going to be taking requests for at least a little while. We'll see how I'm doing on the awake front, probably around 12, and then if I'm still doing alright, we might jump into a game. So, see how things go. I want to say Elite Dangerous still has 16 hours left on the community goal. I have no idea if the community is actually going to make it this time. If there only was software that could solve matrix math easy. Alright, you know what? I'm not wearing my MATLAB shirt today, but nonetheless. Oh yeah, somebody else did this yesterday. Because I most definitely did not properly. Meh. Pretty much guarantee this is wrong, but whatever. It's fine. No, no. Yeah, no. I do actually have... Oh, wait. Hey, there we go. Yep. Oh, yeah, I changed up the last one. Just made it t to the fourth. So if this was e to the 4t, this was 8 e to the negative 3t. Ugh. All right, that was the problem with this one. It was really disgusting about it. So let it be in terms of negative 1 plus e to the 4t times e to the negative 3t. Like, why would you do that? There is a way in which we made something very similar work for us as well today when we were doing variation of parameters. I don't really feel like going into octave either. Yeah, I tried installing DaVinci Resolve as also last night, and just like it got way too complicated. But I was also just really late, and I didn't really care all that much. Having problems trying to figure it out on Ubuntu, which I'll grant you, a lot of people have been saying that might be part of your problem. I don't really want to have to install something else. Okay. Well, that's not really working for us. And nobody's requested anything, so I think we're going to call that section. And let's do let's try something here. Oh, you know what? We're gonna play Link It 2 because the full version came out. We played this as a demo as part of Next Fest, and I thought it was rather charming, and it came out with this it really just struck me. And the full version came out a couple days ago, and I said, yeah, absolutely, let's get it.